This video is an example of using an RC filter to recenter a signal at a specified voltage. It corresponds to section 11.6 of the Applied Analog Electronics textbook. What is the problem we're facing here? Well, basically we've got a signal that's got a DC bias that's not the DC bias we want. It's centered at some voltage, we want it centered at a different voltage. So we have to block the DC that's there and provide a new DC reference voltage. And that's basically done with just a simple high-pass filter. So we can do that something like this. If Vref is the voltage we want to center at, then this filter will block the DC bias that's coming in and recenter things at Vref. All we need to do is pick an R and a C that are appropriate to let through the signals that we do want to see. There's some frequency above which we don't want to think of that as DC anymore. We want to think of that's our signal. We want to let it through. So we pick RC to do that. Well, that's great if we have a voltage source for Vref that can provide us current to recenter the signal. And sometimes we will. In fact, later on in the course, we'll see how to build such voltage references for whatever voltages we need. But there's a way we can do it with just the power supply. Let's say we want to center at 3 volts. But our power supply is at 5 volts. How can we do that without having to invoke a magic, we got a 3 volts from somewhere? Well, one way we can do that is to put in a voltage divider. Now this voltage divider can provide a voltage at 3 volts if we pick appropriate ratio of resistors. What ratio is that going to be? Well, we need the thing on the bottom to have 3/5 of the total resistance in order to have 3/5 of the total voltage. So if we make this one be 3 times some constant R, and this one be 2 times some constant R, then the voltage out here will be centered at 3 volts. And once again, we're done. Except you can't build something which just has algebraic things like C in them. You've got to know what values you actually want to use. So we need to have something to choose that resistor and that capacitor, those pair of resistors now. And we also need to know, well, what frequencies does it pass? What's the corner frequency? All that sort of thing. And we can do that by saying, well, what's this circuit equivalent to? It's like some circuit like this. And we can go back to what's the Thevenin equivalent for this simple voltage divider here and just replace that conceptually. So we can say, well, this is going to be the equivalent of a resistor to some voltage. What voltage? Well, that voltage is going to be the voltage from this voltage divider. 5 volts times 3R over 2R plus 3R, or 3 volts. Okay, so that's as if we had a 3 volt voltage reference coming in. What's this resistance going to be? If you go back to our Thevenin equivalent of a voltage divider, that's going to be these 2 resistors in parallel. So that's going to be 1 over 2R plus 1 over 3R. So that's 3, 6, and 2, 6, 5, 6. Invert that, and we're going to get 6/5 R or 1.2 R. Okay, so we've got a capacitor and a 1.2 R resistor is their equivalent circuit. All right, if we know the corner frequency, we could pick RC from the corner frequency, but we're not always going to be specified a corner frequency. There's other ways to specify what the gain has to be. And I'm going to pick a slightly more complicated way to do it here, because you might have to be worrying about things like, hey, I'm trying to attenuate a particular signal this much. I'll show you how to do that now, rather than having to say just corner frequency is all I know how to do. So let's say we want to attenuate, and by a factor of 5 at 1 hertz. Okay, so we've got a high pass filter here, and we're saying the gain at 1 hertz, the gain is approximately 0.2. All right. Well, what is the gain of this filter? It's just a voltage divider with a capacitor on the input and a resistor going to a DC source. So that's going to have a gain of, well, 1.2 R is to the DC, and on the combined is 1.2 R plus 1 over J omega C. And what I want is that when omega equals 2 pi radians per second, then I want the magnitude of the gain to be approximately 0.2. Okay? So we need to figure out what's the magnitude of this thing. It's kind of messy looking there. So let's not have R in there twice. Let's just divide top and bottom by 1.2 R. So I'll have 1 over 1 plus 1 over J times 2 pi per second, 1.2 RC. And sorry, that's the gain. We're interested in the magnitude of the gain. We can flip this thing upside down because this was the gain. This thing's got to be about 0.2. We can flip this thing upside down and say 5 is approximately the magnitude of 1 plus 1 over J, 2 pi per second, 1.2 RC. And it looks like I'm running out of paper here, so let's start over again with another piece of paper. Magnitude of this thing. A little bit messy to work out. Let's apply Pythagoras' rule. 25 is equal to 1 plus 1 over 2 pi per second, 1.2 RC squared. Okay, now I can simplify this because I can subtract the 1 from both sides, take the square root of both sides, flip it upside down, and I get something like 1 over 24 equals, well, I'll take the square root to get 2 pi per second, 1.2 RC. And at this point, I think I can go to a calculator and do it numerically. 24, 1 over x square root, 2 divide pi divide 1.2 divide, and I get RC is approximately 27.07 milliseconds. Okay, now what do I have to do? I've only got RC. I need R and C separately. For that matter, I don't even need R. What I need is 2R and 3R, because those are the sizes of my resistors. So at this point, there's a lot of trade-offs. If I make the resistors very large, I can make the capacitors small. Making the resistors large means I don't have much current through that voltage divider. Remember, I've got a voltage divider here, and any current that's going from 5 volts to ground is basically being wasted. It's just heating up those resistors. So I probably want these resistors to be pretty big, and the capacitor should be pretty small, as long as we've got approximately this RC time constant. And I picked an arbitrary value for a capacitor. Actually, I don't remember how I did this problem originally. I might have picked the resistors first and come up with the capacitors. But I'll do it the other way around this time. I'll say, let's pick C to be 560 nanofarads. Then, if I divide this by 560 nanofarads, I get R is approximately 48k ohms. But like I said, I didn't need R, I needed 2R and 3R, and 96, not a very good round number, and these things only had to be approximate, so let's round this to get 2R to be 100k ohms, and 3R to be 150 k ohms. Those are nice round numbers, easy to get on standard resistor values. In fact, I probably, thinking back on it, I probably originally, when I was working out this example, started with these values and came up with a capacitor from that. Because those are nice size also for keeping the current from being too large. So what's our circuit at this point? We've got 5 volts up here. We have 560 nanofarads here. We've got 100 k ohms here, and we have 150 k ohms here. Now, we did a whole bunch of calculator work, a whole bunch of algebra. Is the chance we made it through here without a mistake? Not all that great usually. So I want to do a check. But I want to do the check without going through the same calculations over again, without using the calculator again. What I'm going to do is I'm going to go over to GNU-plot, because GNU-plot will let me do all these calculations in a very straightforward way. So let's see, get over to the terminal, GNU-plot. All right, first thing I want to do is to load the definitions.gnuplot file that has all my functions in it for defining impedance of capacitors and voltage dividers and things like that. And then I'm going to type a complicated formula. And I'll walk you through exactly what it is. I'm printing out the absolute value of the output of a voltage divider. Now, the divider formula didn't include a voltage in it, really. It was just the gain of a voltage divider. So that's what I wanted. I wanted this gain, if I've set up the right voltage divider here, to be 0.2 approximately. And on the top, I've got that the impedance of a capacitor at 1 hertz of 560 nanofarads. Okay? That's my top part of my voltage divider. The bottom part of my voltage divider is going to be 2 resistors in parallel, because remember that the equivalent circuit for our voltage divider was to put those 2 resistors in parallel. And that's 100 kilo ohms and 150 kilo ohms. And so all I have to do now is do that. And it says my gain is 0.2065 and a whole bunch more decimal points, which really don't matter. Well, that's very close to the 0.2 that I was looking for, so it looks like I did it correctly. I've got the right gain at 1 hertz. And everything here, I've got the right voltage now coming out, I've got the right gain at 1 hertz, I've got my design. There it is. Now, what made this example more complicated than most of the ones that you'll be doing is that I had specified a gain at 1 hertz that was not that easy to achieve without going through some algebra. Quite often you'll have much easier specs, like somebody will give you the corner frequency, where the gain is approximately 0.7, 1 over the square root of 2. Or somebody will say, I want you to reduce 60 hertz by a factor of 10 or 20. And then you're far enough out on the curve that you can use these straight line approximations that we have. The filter's just behaving like a resistor or just behaving like a capacitor. This is about as complicated an example as you're likely to encounter for this sort of recentering exercise.